Part C, Mergesort. Yeah. So another important sort in this divide and conquer module, 3.1 Introduction to Mergesort. Yeah. All right. Yeah. First, let's look at a simple computing problem: merge two ordered arrays. Yeah. It's a simple problem, but very important for this merge sort. Yeah. Let's look at the question. Given two ordered arrays, order this information. We need to use the question, how to merge them to get an ordered array. Yeah. So simple. Yeah. We need to use the minimum number of comparisons to merge two ordered arrays. Yeah. So it's a very basic question. Yeah. All right. Yeah. First, let me give you the reason why we need to solve this basic problem. Yeah. So let's consider a special situation. Yeah. How to sort a huge array. Yeah. Think about it. Now you need to sort. Your data is, the data size is huge. How large? What do you mean, huge? How large is huge here? Right? Yeah. Here, we need to get an idea. How large is, we mean here. Yeah. So think about when we sort an array, we need to have our data ready on our computer. Right? The data is stored in your computer. You need to get your data ready. Yeah. And your data is stored on the hard drive, right? Hard drive. No? So your data, original data, is stored on a hard disk. Yeah. But when you sort your data, you need to load it into the main memory, right? Yeah. Load your data into the main memory. Look at the size of your main memory. We know the size of the main memory is much smaller than the size of the hard drive, right? Usually. Yeah. So here, we can assume our data, the data size, the size of our original data is greater than the size of the main memory. In that situation, how do you sort your data? Okay? Yeah? Yeah. So let's think about, main memory, RAM, right? Yeah. So we talk about, the RAM size. Yeah. Yeah. For a ordinary computer, yeah. So you can think about 32 gigabytes. Okay? Yeah. 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 Some of computer could be 64 or even larger, right? Yeah. But the size, think about it. If the data size or array, so the size of array is greater than your memory size, RAM size, how can you sort the data? That could happen, yeah. That could happen, although the probability could be very small. Yeah. Yeah, but here, we just think about how to handle large data size. Yeah. We need to have a solution. Yeah. Divide and conquer. Remember, in this module, the title is divide and conquer. Can we use divide and conquer? Can we divide our original data into smaller subarrays? Smaller subarrays. Then we conquer, yeah, conquer for each smaller subarray, we sort it. Okay? Conquer here means we sort subarray. Each subarray, we can sort it. Yeah. All right. So let's divide our original huge array into, multiple segments, and make sure the size of each subarray is less than the size of our RAM. So we can load each subarray into the and run our sort algorithm, get it sorted. See? Yeah. So now, let's assume that after we sort each subarray one by one, so at the end, we get all of them ordered, but just ordered subarrays, right? Our goal is we want to get the whole array ordered. That's our goal. So now the question, how to get a whole array sorted? Each subarray is ordered. Whole array, you cannot load all the subarrays, right? When you load, every time when you load your data, you can only load a portion of data. You cannot load all the data in your main memory. Only small portion of your data that can fit in the main memory. Now you can see we need this. We need to solve this one. Merge two ordered array. Look, for every two adjacent ordered arrays, now we need to merge these two ordered arrays to get a larger ordered array. If you can do it in that way, next time, every time you merge two ordered arrays, all right? Merge, merge, merge. But here you may have a question. When we merge two ordered arrays in a larger ordered array, right? So the larger ordered array may not be able to load it into the main memory sooner or later, right? Don't worry. When we merge two ordered arrays, can we, every time we load a portion of data, we do not have to load the data of the whole subarray, right? We can load a portion of data. So then, put elements in place bit by bit, okay? We do not need to put everything in place. Then, store it, So we can use, when we put elements in place, we can do, small amount every time, So you can handle it. You can handle it, All right, So here you can see, here we need to merge two ordered arrays. So here, although when we split, we can even use parallel computing to speed up the performance. But here, our focus is at the fundamental part, merge two ordered arrays. Now let's try to solve this problem. Now, let's look at the idea. So we need to find appropriate strategy here. We need to take advantage of the structure. The structure, main structure here is the order information. But the question is how to use the order information. All right. So we need to look up useful information in our experience. In our experience, which part is closely related to this question? So we want to borrow some experience from there. All right. So let's look at the sorts we have learned at this point. Selection sort, selection sort does not use the order information, right? Because selection sort no matter what the order is, you're always, finding the minimum. Do it in the same way. Selection sort. Yeah. All right. Bubble sort, we do not use order information. Okay? Yeah. Ascending order, descending order, it doesn't matter. We do the, bubble way. Okay? Swapping. Yeah. So we do not use the order information. Okay? All right. Then insertion sort. Think about insertion sort. When the data is almost ordered, yeah, then the algorithm runs extremely fast, yeah, near the best case. Yeah. So we can see in this insertion sort, yeah, we take advantage of the order information. Yeah, quite a lot. Yeah. So that tells you we should borrow our experience from insertion sort here to solve this basic problem. Okay? All right. Yeah. So next, let's try to understand insertion step and see how can we make it connected to our merge step. Yeah. We want to connect insertion step and merge step. What's the difference? Yeah. All right. Yeah. Here, let's compare insertion step and merge step. All right. Yeah. So for a typical insertion step, let's recall. How did we do the insertion operation? Yeah. All right. So given an ordered array and one element, we want to do the insertion. Yeah. Here you can see, comparing our merging two ordered arrays, the first half is the same, right? Yeah. This array is ordered. Okay? Yeah. When we merge two ordered array, the first array is ordered. For insertion step, the second part of your data, it's a single element. But the merge step, the second part is another ordered array. Yeah. This part is different. Yeah. Different. But we can treat, although this merge step, the second part is different, but this one single element, can we treat it as a special ordered array? Yeah. One element, if we treat it as a special array, one element array, it is ordered, right? Yeah. So we can treat this merge step, our data, the situation is a special case of the merging situation. Yeah. Okay? Yeah. In that kind of view, you can make connection. So you can borrow the implementation details from the insertion step. All right. So now when we do the insertion, so remember we compare B, with the element one by one from one end, from the right end in sequential order. So here we look at the standard insertion step. Standard insertion step. All right. Yeah. All right. So here, our new interpretation. Yeah. All right. So new interpretation, now we need to replace this single V element ordered array by a general new ordered array. Do that replacement. And we need to modify our implementation details. Okay? Yeah. So that's our new view. Okay? So we need to consider our new view. Merge two ordered arrays for a new ordered array. Yeah. The implementation details, we want to modify our old implementation details from the merge step. Yeah. That idea. Yeah. All right. So now we need to consider how to, get a problem solved. Yeah. So the data size kn1, that's the insertion step. Yeah. Using our new merge view to look at the data distribution is not balanced. Right? Yeah, not balanced. Okay. All right. And here, we for this merge sort. So here we need to consider another important question in our merge sort. Why you want to develop another sort algorithm, right? Yeah. So you need to improve the old algorithms, right? Your old sorts. You need to improve. Otherwise, if your new sort has no improvement in any aspect, why you do it? Right? Yeah. So here we need to consider in this new sort, we need to consider the improvement. So this improvement is at the worst case, poor worst case. Yeah. So in our previous, those three old sorts, what's their worst case? Think about it. Their worst case, big theta of n squared, right? Yeah. Big theta of n squared, worst case for all those three sorts. Yeah. It is very bad. That is very bad. Okay? Yeah. So we want to improve it. Yeah. Yeah. We want to make the worst case much faster than this one. Right? Yeah. But to make the worst case faster, we need to work on some special property. We need to improve. We need to know why. Where is the problem? We need to identify that problem first. The problem that caused the worst case. We need to identify it. Then we can fix it. Yeah. All right. The problem we identify is because the data distribution, the data is unbalanced. That's the problem we identify. The reason, poor worst case. Yeah. So the solution is when we have a chance to split our data, divide and conquer. When we divide the data into two subarrays, when we have a chance to split it, we want to do a balanced split to avoid worst case. When you do the evenly split, okay? Yeah, so that's balanced split. Based on our balancing principle, we can avoid the worst case. If we can avoid the extremely unbalanced data split, we can avoid very poor worst case. That's our understanding. Okay? So that's our view. So now let's do it. All right. So here in this merge sort, when we split and given array into two subarrays, we want to do even split. Yeah. All right. Yeah. So Yeah. So that's the, yeah. All right. Yeah. Yeah. Try to make two subarrays of equal size. Because when we have odd number of elements, so we can split to make the difference of the sizes of two subarrays, difference is 1. That's the best we can do. Yeah. All right. Next, C.2, let's study this merge operation, the key operation in solving this problem. Merge operation. All right. So this merge operation, yeah. So let me use a diagram. Yeah. So here, yeah. Oh, first, yeah. Before we work on the merge operation, so let's use the divide and conquer view to see how do we split our data. Yeah. So then we can work on the merge details. All right. Yeah. All right. Yeah. So now let's look at the starting point. This is the starting point. Given an arbitrary array, this line segment represents the whole given data, original data. Yeah. Divide and conquer. The first time we need to divide this whole array into two subarrays. So we split evenly. Yeah. So yeah. Right in the middle. Yeah. You know. Yeah. Median. Yeah. Actually, here we should not call the median. You know, the position in the middle. Yeah. Because median, that's the value, right? We talk about the value in the middle. So here, the position in the median, in the middle. So not the value in the middle. Position in the middle. So it's not a median, okay? That's the first round split. Second round split. So for each subarray, we do another round, evenly split. Second round. Then third round. Yeah. Keep doing the splits until we cannot split anymore. Yeah. When you get one element array, you cannot split. Right? Yeah. So we have to stop. One element subarray. Then you have to stop. Okay? All right. Then now we need to do the merge operation. Yeah. So when we do the merge operation, yeah, we merge two adjacent subarrays. Yeah. When we start, we do the merge operations bottom up. Yeah, bottom up. Yeah, we split. You know, all of our subarrays have very small sizes. Yeah. Yeah. So we merge them from the bottom. So it's a bottom up approach. Next round, yeah, we move two adjacent ordered subarrays. Yeah. Then, yeah, and moving up. Okay. Yeah. At the end, the last one, we only need to move two ordered subarrays to get a whole array ordered. Yeah. So that's divide and conquer approach. Okay? Yeah. From this diagram, you can see if we know how to merge two adjacent ordered arrays, then we can get a whole problem solved. Yeah. So we only need to solve one problem. This problem. Okay? We only need to solve that one. Then the whole merge sort is there. Yeah. And if we do in this way, here you can see our data distribution is quite balanced, right? Yeah. Every time we do even splits, yeah, we always do even splits. So that there is no unbalanced data distribution problem, right? Yeah. Yeah. we hope in this way we can avoid very poor worst case efficiency. Now, later we need to do analysis to see it. So here we just based on our understanding of the data. So we should have a good chance to avoid poor worst case. Yeah. All right. Yeah. Next, now we need to work on our main step, the merge step, the details. Yeah. All right. Yeah. So let me use another diagram to consider the merging details. Yeah. Merge details. All right. A subarray, B subarray. Two subarrays. They are both ordered. Yeah. All right. Then, for the first comparison, okay, all right, here, when we start, let's think about our goal. We want to get a destination array. Yeah. So in our destination array, all the elements in our destination array are in place, right? Yeah. So here we use this in place concept to view this merge step. In place. All right. So our goal, we want to make all the elements in place. That's the goal. All right? Yeah. So in our first comparison, let's look at our first comparison. When we do the first comparison, can we, after the comparison, can we make in place? Yeah. If we can, that means we make progress. Yeah. The first one, we get one element in place. Second one, we get another element in place, and so on. Yeah. Then, that would be great. Okay? Yeah, every comparison, we can make some progress. Yeah. All right. So here you can see our first comparison. Let's compare A0 and B0. A0 is the minimum of the first subarray. B0 is the minimum of the second subarray. So after one comparison, the smaller one must be the minimum of the whole array. Minimum of the whole array. Then you can put it in place because you find the minimum. You find the global minimum. Then you just put it in place immediately, right? Yeah. So you can see the first comparison. Here we use this notation min 0 to represent the minimum of A0 and B0. Okay, all right. Yeah. Max 0 equals the maximum of the A0 and the B0. So the min 0, we can put it in place in our destination array. Yeah. Yeah. The first element is in place. That's our progress. Yeah. All right. But the max 0, we don't know if it is in place, right? Yeah. It may not be in place. Yeah. We don't know. Yeah. Because we need to consider if there are other possible elements that are smaller than this max 0. Yeah. So here, the next element, let me use, in order to reduce the uncertainty, okay? Yeah. In our discussion, I want to make our understanding a little easier. I try to reduce the uncertainty. Let's consider this case 1. Yeah. B0 is the max 0, this case. Yeah. Because the other case is similar. Yeah. So B0 is this max 0. Okay? That means we should put A0 in the first position of the destination array. All right. Then B0, the next comparison, yeah. So B0 has a chance to be the next element in place, right? But there is another candidate, A1. A1 is the other candidate. Yeah. A2 will not be the candidate, right? Because A2 is greater than A1. So A1, only A1 is the other candidate. So B0 and A1, two candidates for the next element in place. All right? So our second comparison is between A1 and B0. Okay? So let me use min 1 as the minimum of A1 and B0. Okay? So after our second comparison, min 1, another element is in place. Okay? All right. Yeah. So can you follow this implementation idea to put all the elements in place? Yeah. Yeah. If B0 is in place, then A1 is one of the two candidates. B1 is the other candidate, right? Yeah. So you just, using the, the minimum, the local maximum. The local maximum is one of the two candidates for the next comparison. The other one is the first element in the other subarray, right? First element in the other subarray, the other candidate. So every time you have two candidates for the next element in place. Yeah. So now you keep doing, adding, yeah. So one element in place, yeah. But this time, when we consider putting all the elements in place, there are different cases, right? Now let's consider the worst case first. Yeah. Under what situation we will get this worst case? Yeah. Yeah. Then best case. Now we consider the worst case. Yeah. So we put element by element in places. Yeah. Can you imagine under what situation? Yeah. Because the worst case corresponds to the maximum number of comparisons where we do this kind of comparisons. So can you imagine under the worst case, because we want to make the maximum number of comparisons. Can you imagine? What's that situation? So, yeah, that means you need to do the comparison. What is the last comparison you need to do? Last comparison is put this element in place, right? Yeah. Yeah. That means you need to do one comparison to put one element in this one. Yeah. Because the final element, you never need to do comparison, right? Final element, only one position left. With one element, you just drop the last element there. No comparison. Okay? Yeah. So this last position, no comparison. So no comparison. But this one, this position, sometimes you need to do comparison. Sometimes you do not need to do comparison, right? The second to last position, yeah? Because sometimes, if you can find two candidates, yeah, yeah, one candidate, so each candidate from one of the two subarrays, if you can have that, yeah. So yeah, here, let me explain. So this one, there are two possibilities. Okay? Two possibilities. All right. One possibility is you have elements, candidate. Yeah, so here, let's consider candidates. Candidates, okay, all right. Candidates, if you have one element, A sub I, and a B sub J, yeah, one element from A sub A, one element, then you need to do comparison, right? Yeah, then you need to do comparison. But if you have AI plus 1 or BJ plus 1, then no comparison not needed, right? Comparison not needed, right? Yeah. So here you have these two possible cases. Yeah. But the worst case, this is the worst case. Okay? Yeah. One element from A subarray, another element from B subarray. Yeah. Because if all the remaining elements from A subarray, you don't need a comparison, right? Because they're ordered. Your remaining data already ordered. Or all the remaining data in the B subarray, you don't need to do any comparison because all the remaining data already ordered. You just put them right in place. Okay? All right. But this one, you don't know which one is larger, which one is small. So you need one more comparison. So the worst case should correspond to this situation. You need your final comparison here. Yeah. All right. Now the conclusion, based on this understanding, we need to count the total number of comparisons. Yeah. So we do comparison from the beginning all the way down to the second to last position. Yeah. Each position we need one comparison. So we only need to count the number of positions up to the second to last position. Yeah. Only remove the last position. No comparison needed for the last position. Yeah. Can you tell me? Yeah. So yeah, here I need to give you look at the size. The first subarray, the size is K, right? Yeah. Yeah, because you look at the subscript. Look at the subscript, you know the data size. The first subarray data size is K. Second subarray data size also K, right? Yeah. So you know the total number of elements in these two subarrays, right? 2K. 2K. Now can you tell me, for the worst case, how many comparisons do we need? Yeah. Look at the positions, yeah, corresponding to total number of elements. Can you get the answer immediately? Right? Yeah. Yeah. Or you can also look at the subscript, right? 0, 1, the subscript, 2K minus 2, right? Yeah. Yeah. So you can see, yeah, the number of comparisons for the worst case, 2K minus 1. Yeah. So let me erase this part. 2K minus 1. The answer. Yeah. All right. Yeah. Yeah. Worst case. Okay. All right. Next. Yeah. Next. Still worst case, but this time we want to consider the general merge step. Yeah. For the general merge step, we do not require our two subarrays have the equal size. We do not require it. Okay? So the first one, the size of the first subarray, m elements. The second one, subarray, n elements. They could be different. Yeah. So in this situation, for the worst case, how many comparisons do we need? Yeah. Similar analysis, but when we do the counting, slightly different. Yeah. Yeah. Can you get the answer quickly? Yeah. The answer, number of comparisons for worst case. Yeah. All right. You can use subscripts. You can use total number of elements minus 1. Yeah. The answer is m plus n minus 1. Okay. Total number of elements, n plus n. But you need to minus 1. Yeah. Exclude the last position. Don't need any comparison. Okay. That's the worst case. All right. Then, best case. Yeah. We also need to consider the best case. All right. Now, the best case, let's only do the general best case. Yeah. For that even case, you know, after we get a general best case, we can easily get a special best case easily. All right. So for the general case, this time, our goal, we want to consider a special situation that we need a minimum number of comparisons. Minimum number of comparisons. That's the best case. Okay? All right. So can you imagine some special data input that would result in minimum number of comparisons? Think about that. Yeah. That means you want to leave as many elements as possible in the tail part. Yeah, the tail part that you do not need a comparison. Okay? You can put them in place without any comparison for the tail part. Okay? Yeah. Yeah. For the head part, yeah, when you start, you need to do comparisons, right? Yeah. So then, you know, after some point, suddenly you reach a special tail situation that no comparison is needed. That's easy. Huh? From our worst case analysis, we already see the tail situation should correspond to two possible tail situations, right? One is AI plus 1, yeah, all the way to the end, right? The other is or bj plus 1 all the way to the end. Okay? Yeah. In these one of the two cases, that no comparison needed in the tail part. You just copy these elements, put them in place immediately. All right. Now, based on that understanding, yeah, the best case should correspond to either this A tail case, right, or B tail case, right? A tail case, you want this A tail as long as possible, right? Yeah, the A tail. The longer, the better, right? For the B tail case, the longer the B tail, the better, right? Yeah. All right. So then, yeah, so you can see, yeah, the longest situation. Yeah. So for this case, the longest is the longest case, longest. The whole, is it the whole A, here, A subarray, right? For this case, the longest whole B subarray, right? Whole B subarray. Right? Yeah. See? Yeah, that's the longest, right? Yeah. Yeah. So for the A case, yeah, the whole A subarray is used as a test. That means the first A element beats all the elements in B subarray, right? Yeah. The very first element in A subarray already beats all the elements in B subarray, right? That's the A case. For this B case, the first element in B subarray already beats all the elements in A subarray. Okay? Yeah? Yeah. All right. So you have these two cases you can consider. Yeah. Yeah. Try to exhaust one of the two arrays as early as possible. Yeah? Yeah. When you use the first element of A subarray to beat all the elements in B subarray, that means you already put all the elements of B subarray in place as early as possible, right? Yeah. So, yeah, the first element in each subarray already, after comparisons, to put all the elements in B subarray in place. So it will exhaust the B subarray as early as possible. Yeah. The other one is the first element in B subarray can already exhaust all the elements in B subarray as early as possible. Right? Yeah. So these two cases you need to consider. All right? Yeah. Yeah. All right. These two cases, one is better than the other, right? Yeah. So which one is better? Yeah. Exhaust the shorter array. Shorter array, that means you need to do fewer number of comparisons. So you have a longer subarray, you have a shorter subarray, right? Yeah. So you want to exhaust the shortest subarray because you only need to do the comparisons as the number of elements in the shorter subarray. Right? Yeah. All right. So based on this understanding, so we have our conclusion. The best case efficiency is the minimum of m and n. So we have these two formulas. Yeah. Worst case and best case merge for this merge step. Yeah. These two formulas. Yeah. Minimum of m and n. All right. Yeah. So we complete this merge operation. Then, based on our analysis before, we complete the whole merge sort, right? Yeah. We complete the whole merge sort. Yeah. Divide and conquer. Yeah. When you merge two adjacent subarrays, you use this merge step to merge. Okay? Yeah. All right. But then, next, we need to look at the efficiency analysis for merge sort. Yeah. Remember, one of our design goals, we want to avoid poor efficiency. Yeah. Here, we want to see if we can really avoid the poor efficiency. So let's look at the analysis part. Yeah. Derive recurrence relation. Yeah. All right. So here, yeah, we estimate the worst case efficiency. Yeah. So here we just do some very rough estimate. Yeah. To get some general idea. Yeah. All right. Yeah. Let's consider a given array, yeah, and we use this capital T function to represent the total number of comparisons to apply the merge sort on this array. TLB, yeah. Then divide and conquer. Okay? Yeah. All right. So divide and conquer, make even split. Yeah. So the half size, each one, half of the size, Yeah, approximately. Right? Yeah. So we do some estimate. Yeah. All right. Then to sort the first subarray, yeah, we use capital T of n over 2. This many comparisons. Yeah. Second, also T of n over 2. This many comparisons. Yeah. But there is a merge step, right? Merge step. Here, when we do the merge operation, we use the worst case formula. We have worst case formula, right? So the worst case. All right. The worst case formula, we know the worst case formula tells us it's n minus 1, right? Yeah. Total number of elements n minus 1. Yeah. But here, because this minus 1 is a very small number, yeah, we just do estimate. So for convenience, we use n. Okay? Yeah. So we don't need to worry about that minus 1. Okay? Yeah. Yeah. Because it's a rough estimate. Okay? Yeah. Only one difference. Yeah. All right. Yeah. Now we can write recurrence relation. Yeah. Yeah. Two base cases we know easily. Then our main recurrence relation is this one. All right. Okay. So then we need to do some rough estimate. Okay. Yeah. All right. Yeah. Yeah. Rough estimate, we consider a simpler case that the simplest possible case here, n is power of 2. That's the simplest. Power of 2. That means every time when we do division by 2, we get an integer. Okay? Yeah. We get an integer. The power of 2. Yeah. All right. Yeah. So that special case should give us some general idea, the trend. Yeah. All right. N equals 2 to the k. Yeah. Then, let's plug in. Yeah. So we can remove all division by 2. So the first equation, like this. Yeah. Yeah. All right. Now, we want to get more general information. Yeah. So we want to do some algebraic operation on this equation. Yeah. All right. So here we apply the division method. Division method. Yeah. Yeah. So, yeah. Here you need to have some experience. Yeah. In problem solving, this step, yeah. If you want to ask question, how do you know? You need to apply division method here, yeah. Because you need to have some experience. Okay? All right. Yeah. So you see a lot of power of 2, right? You see a lot of power of 2. Yeah. So you want to do something based on power of 2. Right. Yeah. So here we do division by 2 to the k, both sides. Yeah. All right. So now you see this new representation. Yeah. Yeah. This new representation has some special property. We can take advantage of it. Yeah. So what's the special property? Look at the two fractions, left-hand side, right-hand side. They have the similar structure, right? Yeah. The structure, similar structure. Only difference is the exponent number you change from k minus 1 to k. That's the only difference. Yeah. Other than the exponent numbers, they are the same. Okay? Wise. Yeah. All right. So then we work on the structure. So we define a new function. This function, yeah. So what's the definition of function? Yeah. This g function, g of k equals t of 2 to the k over 2 to the k. Yeah. So we get a simpler g function. Yeah. G of k. Yeah. Yeah. All right. With this g function, we can simplify our original formula. Simplify. Okay. All right. So let's simplify our original formula with g function. Yeah. Substitution. Yeah. With g function. All right. With g function, our equation becomes g of k equals g of k minus 1 plus 1. The equation much simpler, right? Yeah. So it's a very simple recurrence relation. So let's apply it another time. Yeah. All right. Yeah. The initial value we need to use g of 1 equals t of 2. T of 2 is 1, so 1 over 2, yeah, 1/2. Yeah. All right. So then the next equation, when we apply this recurrence relation, g of k minus 2 plus 2. Yeah, yeah, because this g of k minus 1, yeah, we do another recurrence relation, equals g of k minus 2 plus 1. So 1 plus this 1, we get this 2. Okay, all right. Yeah. Can we see some special rule? Yeah. So we keep doing things like this. Yeah. Yeah. All right? Yeah. Keep doing things. Yeah. So the first one, k minus 1, then you plus 1. K minus 2, you plus 2. K minus 3, you plus 3, and so on, right? Yeah. K minus 1, another k minus 1, yeah? Because the last one is g of 1, right? The last one, here, the invariant, the size plus constant, yeah. That's k, the size plus constant. We can use this invariant to keep track of the data, right? Yeah. Yeah. So that invariant equals k. Yeah. When we reach the bottom, g of 1, then the constant part should be k minus 1. The size is 1. When the size equals 1, the constant term should be k minus 1. Yeah. But that is 1/2, right? We know 1/2. So k minus 1/2. Yeah. So this g of k equals k minus 1/2. But we need to go back to the t function. Yeah. Go back to the t function. So t of 2 to the k equals, parenthesis, k minus 1/2 times 2 to the k. After simplification, yeah, n equals 2 to the k. Yeah. K equals log base 2 of n. Right? Yeah. Yeah. Then you can see t of n approximately equal to n times log base 2 of n, right? Yeah, here, approximately, okay? So n here, this parenthesis corresponds to log base 2 of n. This, yeah. Minus 1/2 we can ignore, right? Minus 1/2, too small, we can ignore. Yeah. So k corresponds to log base 2 of n. Yeah, so this LG, yeah, so in computer science, our default base is 2. Yeah. In math, this LG, the default base is 10. Yeah. Yeah, but in CS, it is 2. Okay? So log base 2 of n. Okay? Yeah. Yeah. Now, you can see we get an estimate for the worst case. The worst case, remember, we want to avoid the poor worst case, right? Our goal, avoid the poor worst case. The poor, that is big theta of n squared, right? Yeah. Here, we make it. We get n log n. Yeah. So that's a big improvement. Yeah. So for the merge sort, the worst case is big theta of n log n. N log n. Okay? Yeah. All right. Yeah. Yeah. All right. Yeah. So here, yeah, so we complete the merge sort. Yeah, yeah, yeah. The last topic is the problem solving. So we leave next time. So yeah. Now we summarize a little bit. Yeah. So the merge sort. Yeah. All right. Yeah. From the algorithm, the merge sort, you can see our main focus, we want to avoid poor worst case efficiency. Yeah. How to avoid it? We distribute our data evenly. Yeah. Because we have the freedom to distribute our data, to split our data. Yeah. Sometimes you may not have the freedom. In our next part D, about the quick sort, you do not have the freedom to choose how to split your data. Fortunately, here, we have that freedom. So we use this freedom to split the data evenly. The immediate result is we control the worst case. The worst case, not very bad. Okay, N log N, pretty good. Yeah, pretty good. Yeah. All right. But the next one, the quick sort, when we go to, because we do not have the freedom to control how to split, we have to accept it, whatever given us. So the result is the quick sort cannot avoid poor worst case. Okay, that's the difference. Yeah. All right, yeah, so next time we will do the quick sort.